I had motivated you formal methods, and we had introduced this most elementary model for doing verification, what we call a transition system. If you search for it in the literature, there'll be a few other names for it. They'll be called finite state systems. Then Kripke structures is another name for the same thing, because these were introduced by this person called Saul Kripke, so they're named after him as Kripke structures. But basically what it has is it's a graph. The nodes of the graph, we call them states, representing a state of a system, and the edges of the graphs take you from one state to another, and they take you always because the system is acting, the system is doing something, is pursuing an action. So the set of transitions, they are called, tells you from a particular state, when an action happens, how the system changes its state, right? And then there is always a set of states to begin with, and these are labels, basically a set of Boolean entities, true, false entities, atomic propositions that label the states, that a set of atomic propositions. So read this as a set of atomic propositions that come as a label for every state, that tell you what is true in a state and what is not true. Whatever is not there in the label doesn't hold in a state, and whatever is there in the label holds in the state. So this was a toy example of a very high abstraction of a beverage vending machine transition system that we saw yesterday. And what are the properties that we would like to verify? We briefly described them as what I call reachability properties. So you would want to say that at any point in time a coffee or a tea is delivered only if a coin is inserted. And if a coin is inserted, then in the next state a coffee or tea is delivered. These are the kinds of properties, and most of them can be accomplished by doing some kind of a traversal in the underlying graph of the transition system. So that's about what we saw yesterday. Then yeah, we saw an example of, so they're very good in modeling hardware circuits. This is probably the most successful use of model checking per se. So what we will see now is extensions of transition systems. The one we saw for beverage vending machine, all of you would agree that was a very, coarse abstraction, right? It hardly had any details. For example, did we say how many cups of coffee or tea totally a particular vending machine could deliver? Somebody should refill milk or coffee powder or whatever. When it gets over, the beverage vending machine must be able to say that I have run out of stock, come and refill. We just said that, we basically said some very elementary properties about its correctness. We didn't really describe its behavior fully, right? So obviously it was a very high level abstraction, not going to be able to scale up to the kind of models that I was talking to you about. I said Mars rover, power window controller, obviously no. Now, we talked about big examples, but we saw a very tiny example, right? So just by using transition systems as we saw here, we're not going to be able to model and model check all kinds of realistic systems. So what are the extensions that are there? So today I'll give you examples of two different kinds of extensions. Obviously it doesn't end there, there will be some more also, but we'll just look at two. So if we want to extend, so assuming that we keep this beverage vending machine as our example, and if we want to continue to look at it, what are the things that we could extend it with? Obviously we could extend it with a lot of things, but let's say we want to, I've chosen this particular extension because I want to bring in a particular notion. So one simple thing is that, can I know how many cups of coffee or tea will it deliver? Maybe it will deliver 100 cups. And then the way it goes is that, from 11 to 12, 11 to 1:30, all the 100 cups will get over and somebody must replenish it. Maybe during holidays, it's okay to replenish it once a day. Something like that, right? I need to know. And then when a cup of tea is delivered, somebody must reduce one from the count that it delivers. So basically it helps, I can specify a little more behavior, a little more requirements about the system. Once I have a variable that counts the number of coffee or tea, and basically it returns. The other thing is that it must return the coin to the user if it ran out of coffee or tea, or it must say that, no more coffee, tea available, kind of thing. So I would like to model these kinds of things. So to be able to model these kinds of things, you'll realize that earlier we just had actions in our transition system. It said select and, get tea, get coffee. Obviously just that is not going to be enough. We need some conditions. What are the conditions? You see there is an if statement here, right? If there is no coffee or tea, return coin. Right? So this is what I mean by conditions. So we need some conditions to be able to, so we say that transitions execute provided a condition or a guard associated with the transition is true, and when it executes, an set of actions hold, right? So this is how conditions in general are given. So they take this form. So G is a guard. Guard, you can think of it like a simple condition. If you're confused about what conditions could be, you think of it as conditions that involve standard relational and logical expressions in any programming language. If you take a programming language like C or whatever it is, you have the standard logical expressions and or not, the standard relational operators equal to, not equal to, less than, less nor equal to, greater nor equal to, right? This is just that. The syntax of the guards is just that. In formal methods, we call it predicate logic. But in programming terms, you would call it logical and relational expressions. But it's just that. There are a set of variables, then there is a guard or a condition that talks about what the variable is. Right? Obviously, it has to satisfy a few conditions. So we will see. So this for the beverage vending example, this is how it should be. So initially, there's nothing to do. So there is no guard, no specific guard. We can't say that there is no guard. So you say the guard is always true. So true is the Boolean constant true. So when I have predicate logic, every predicate is supposed to evaluate to true or false, right? That's how we use them in programming. So this is the Boolean constant true. So if there is no guard, I will write it as true, which means implicitly that there is a guard which is always true. Or it's the same as saying there's no guard, right? So you just write it as true. So to start with, there's nothing. So you, nothing needs to be true, so a coin is inserted. And similarly, to start with, there could be no coffee or tea, so I could refill the machine, right? I could refill whatever ingredients that are there for the machine. Then there could be a condition which says, let's say, which counts the number of cups of tea left, call it NT, which is the number of cups of tea left in the machine to be delivered. So you said if the number of cups of tea is greater than 0, then the action get tea is enabled. You're able to read this guard. So from the state select, when the number of cups of tea is greater than 0, then I can do get tea and go back to start. So similarly here, so this means that there is no coffee or tea, so which means the number of cups of tea is 0. This is the logical and. In programming language, we write it like this and, right? It's the same and. So in logic, we like to write it. So our normal and operator, which we typically write like this in programming languages, we write like this in logic. So the or operator, which we write like this, we write like this in logic. And then the negation. Different programming languages offer, but some of them might write like this. In logic, we write like this, right? So that's the symbol. So it says if the number of cups of tea equal to 0 and the number of cups of coffee equal to 0, then the action return coin is enabled. You're able to understand? So earlier I just had a model where, a highly abstract model where I just said some actions were enabled like this. From the state pay, I do insert coin, go to select, I do nothing, go to T. But this we realized was too shallow a model. It didn't have enough details. So I added variables to the model, and once I add variables, I'll have guards labeling the transitions that will tell you, which are basically predicates on the variables, relational and logical expressions on the variables that evaluate to true or false. Whenever the guard is true, the action will be enabled. Whenever the guard is false, the machine gets stuck there. Nothing happens to it, right? So in general, transition systems can have variables. So when they have variables, we call them program graphs, because this is just a name. You can still continue to call them transition systems. It doesn't matter. So there is a set of variables, call it this, VAR. Obviously, like in programming, when we have a set of variables, I'm talking about the type of a variable, because I can't compare a variable with another constant whose type mismatches. I can't compare a Boolean variable to check if its value is greater than 5. Right? I can compare it only with true or false. So every variable has types. Again, these are very similar to programming. It could be Boolean, character, integer, whatever. So any other types that you want, you can add. Then the type of the variable will influence the domain of the variable. Like for example, if it's an integer and you're talking about a processor that is 64-bit, yesterday we discussed, that's the domain. That's the set of values that it can take. If it's Boolean, then its domain, whatever it is only 2. true or false, and it goes on like this. Floating point numbers have a very specific implementation in computers, so it will take a domain like that. Each variable will have a domain dictated by its type, and each variable can have a set of evaluations. So for example, we write it like this: evaluation of a variable denotes the set of evaluations that assign values to variables. Like for example, I could assign, if it's an integer variable, I could assign it 3. I can't assign it 3.5. If it's a floating point variable, then I can't assign it 3, I should assign it a 3.0 or 3.2. That's what we mean by an evaluation. And then I have a set of conditions over the variables, which are a lot like, exactly like the programming language if statement conditions that we will write. So how do I read this? You read this as x minus x and x prime are two variables, and x minus x prime is bounded from below by -3 and bounded from above by 3. And x is less than or equal to 2 into x prime, and y could be a string or something like that. Y says green. Is this clear? So this is how conditions look like. So now, because I have variables, I'm talking about particular kinds of transition systems called program graphs. So they're still graphs. We still have states. We still have transitions. The only extra thing that they have is they have a whole set of variables that are around them. So maybe before I explain this, I will show. So I don't think I have a figure for a program graph of a vending machine. Yeah, I don't have it. Okay. So basically it is like a graph. So earlier what did I have? So I'll just draw one sample. I had two states, and then I could have a transition. So let's say this is state P, this is state Q. I could have an action A. So this is elementary. So now what I have a state P, I have a state Q, then I have a guard, and then when the guard is true, I can say a set of actions. So this guard implicitly comes from a set of variables with their types. And then there is logic. So what are the logical operators? There is arithmetic. I can do plus, minus, dot, slash, mod, less than or equal to, greater than or equal to. So I can do relational, and I can do Boolean. This is the logic that I operate over, right? So we say if this guard, this is supposed to be evaluated to true or false. If this is true, then the action is enabled, so it changes state. So the graph looks like this. Instead of having just states and actions, it has set of states, and transitions have two tuples as labels in them, right? What will happen, like for example, I'll show you examples of transitions. Like, so I haven't drawn it, but I've specified, like if you take the same beverage vending machine example, there are basically two variables for now. The number of cups of coffee and the number of cups of tea. Let's say somebody gives you a constant called max, which is the maximum number of cups of coffee or tea that the vending machine can hold. So the number of cups of coffee and tea could vary between 0 and the maximum number, right? So what could be actions? They are the same. There is get coffee, get tea, insert coin. And then in addition, now we have two other actions. If there is no more coffee or tea left, you could do refill. And you should return the coin. Those are these two actions. And this is again just a terminology that is standardly followed in books and this thing. Earlier we were calling them states. Now we will call them locations. It's the same thing. It's just a node in the graph. There is nothing to worry about it. And then what will happen? If I do the action get coffee, then its effect will be the number of cups of coffee gets reduced by 1. If I do the action get tea, then its effect would be the number of cups of tea gets reduced by 1. If I do refill, then both the number of cups of coffee and the number of cups of tea become maximum, right? So these are the effects. So in general, from a state P to a state Q, when the guard is true, I do an action. An action could mean doing an action like this, which is represented about what happens. It also means that certain variables will change values. Is this clear? Like in this case, with this action get coffee, this variable changes the value. With the action get tea, this variable changes the value. With the action refill, both these variables change the value. Is this clear? So it goes on. So with the action coin and with the action return coin, nothing happens. No change happens. That's what the first one says, right? So there are states, there are transitions that fire when when a guard is true. Actions result in change of values of certain variables. So this is what is a program graph. So in general you describe it like this. So LOC is a set of locations. This is a set of actions. And what happens in a transition function? From a location, when a condition on variable is true, you can go to another location. Right? Read this three product as that. There is a set of initial locations. And what is condition? There is a set of initial conditions. And then when an action happens because of change of location, the values of certain variables also change. That's what this is. When an action happens, certain variables which had values will change their values. Right? So this is how a program graph looks like. Right? I haven't drawn the program graph corresponding to a beverage vending machine because I think it was getting to be cumbersome to put it in a slide, but you're able to understand how the graph would look like, right? So it will look a lot like this graph, but slightly bigger, and will have more decorations on its transitions in terms of guards and actions. So this is a program graph, and I want to be able to do the same thing. I want to be able to now check whether certain requirements are true or not automatically, right? So again, I want to be able to use reachability to check if certain requirements are true or not automatically. So what would a requirement be like? Requirements are now like this, right? If a cup of coffee is delivered, then the number of cups of coffee goes reduced by 1. Eventually, number of cups of coffee or number of cups of tea should become 0. You know, the word eventually means sooner or later, right? You're able to understand. So things like this. If the user chooses tea, then in the next state, tea is delivered and the number of cups of tea is reduced by 1. So these are the requirements that I want to be able to do. And I want to be able to do the same reachability on the graph to be able to verify it. Unfortunately, I can't directly work with the graph, with this graph and do reachability like I did earlier. Can somebody tell me any thoughts on why I can't directly do DFS on the graph? Any thoughts? So you've got a sample of the requirements that we want to verify, and I want to be able to do some kind of graph traversals to verify on this. And I don't have the transition system. I have a slightly more complex graph that talks about variables and all. My claim is I directly cannot take this graph and do reachability algorithms on that graph. Any thoughts? Why? Cycles are okay. I can do traversals. Any other answer?
We have to also do couple of evaluation.
Yeah. So one is you have to do evaluation. Variables change values, and based on the values, the next time the transition is taken, let's say if it's a part of a cycle, it may or may not be taken, right? So the graph can be thought of as a purely syntactic entity, right? The syntactic, what I mean by syntactic entity is that it just describes the structure. The actual behavior is when somebody delivers coffee or tea, what happens? The number gets reduced by 1, the number gets reduced by 1. So the actual behavior or semantics or meaning of the graph needs to be derived from the graph. One classical thing that we do in the graph, and the biggest problem why this meaning needs to be derived is the presence of cycles, because when I have a cycle, the thing changes. Evaluation could change at every iteration in the cycle. So the standard thing that we do in this kind of, this is not true with anything to do with formal methods, this is just classical software engineering design modeling, is if I have a graph model that talks about variables whose values keep changing, increasing or decreasing, so these things are called strongly connected components. Cycles are layman's terms, so you call them strongly connected components, right? So whenever there is a strongly connected component in the graph, it has the scope of doing it again and again, repetitively, right? So when it does repetitively, and when the transitions here are annotated with values that will change at every time a transition fires, you can't reason about it directly because its values will change. You can't touch it. So the standard trick that we do is fine, you take an unfolding of the graph. So what is an unfolding? Unfolding of a graph is you take each loop or strongly connected component in the graph and unfold it. It's as simple as that, right? Open it out. So if this is P, this is Q, open it out, P, Q, P, Q, P, Q, I go. Now I can reason about this graph. Because here, suppose, let's say, just as an example, this means that you get T. So what will happen here? The number of cups of tea will get reduced, right? This means something. Let's say this means insert coin or something, right? Just for as a hypothetical case. So what will happen here is initially, let's say there were 100 cups of tea. At this stage, it will become 99, and you need that information. Here, you will just have the information saying that whatever that number was, it will get reduced by 1. But that's not enough for you to do reachability. You want to know what that number was and by how much it reduced, correct values, right? So in the next iteration, what will happen of this loop, whatever was 99 would become 98. In this kind of entity, you will not be able to get that information. Maybe you could argue saying that I'll keep a separate table, but you have to do something that represents an unfolding. But practically, you have to unfold a graph. Once you unfold a graph, here you can do reachability. Is this clear? Here you can do some kind of reachability and work it out, right? So there are standard ways of unfolding a graph. I'm not going into how to do unfoldings of graphs and all that stuff. But one thing to remember is that when I have a graph with a single loop or a cycle in it, single strongly connected component in it, its unfolding is going to be an infinite graph. Is that clear? There will not be finite graphs, but that's all right. We don't need the whole unfolded graph. We need what are called prefixes of unfolded graphs to be able to do our analysis. So here is an unfolding of the beverage vending machine. So I hope you can read it. So I'll help you to read it. So if you look at this entity, this rounded rectangular entity, on top there is this label which talks about the label of the state. So this label says start, the machine starts. Then this label says select coffee or tea. So let's say somebody selects tea, then you deliver tea, go back to start. Somebody selects coffee, you deliver coffee, go back to start. So I have unfolded the graph. In the original program graph, there would have been a loop from start to select. In addition to that, you will notice that there are 2 black dots, 2 white dots. Can you tell me what they are? Number of cups of tea and number of cups of coffee. The black dots are for number of cups of tea. The white dots are for the number of cups of coffee, right? So it says from start, and you go to select, it doesn't change because you have not delivered coffee or tea as yet. But somebody chooses to take tea, it changes. Now the number of cups of tea available in the vending machine is just 1. Similarly, if somebody chooses coffee, the number of cups of coffee reduced, the number of cups of tea stays as 2. And then from there on, again for the next one, if I get 1 more tea, that's it, no more tea left. If I get from here coffee, then 1 cup of coffee, 1 cup of tea, you're able to understand, right? It goes on and on and on like this. So this is just for 2 cups of tea, 2 cups of coffee. You can imagine how it will look like if I had 5 cups of tea and 4 cups of coffee, or 5 cups of coffee. It will be a larger unfolding. If I had 100 cups of tea and 100 cups of coffee, you can imagine how the graph will look like. It will be larger than this, right? So this represents an actual transition system on which you can do a reachability analysis to actually say that, for example, when the number of cups of coffee and tea becomes 0, then if somebody chooses whatever, I have to return coin. I think there's a mistake. Somebody enters a coin, I have to return coin. This should be the other way around. I have to return it and go back. And if the number of cups of coffee and tea is 0, then I can do this refill and replenish the coffee or tea. So this is an unfolded program graph where the maximum number of cups of coffee and tea is 2. Just for 2 cups of coffee, 2 cups of tea, it looks so big. So you can imagine, so why does it look so big? Any thoughts? What is this middle structure here? Any thoughts?
Possible state space.
Yeah, possible state space. Any other further elaboration of that term? Recursion. No, it may not be related to recursion. There's one term that I'm looking for. Yeah. Yeah. So what does that expansion represent? So simple concept in discrete maths. So if you have 2 cups of tea and 2 cups of coffee, how many different ways in which you will choose, and you're allowed to choose 1 cup at a time, how many ways in which you will do to get 0 cups of coffee, 0 cups of tea? Permutation, combination kind of thing. And you know that that's not an easy number. N choose R, N P R, both of them are big. They are factorial in order, right? So it will be big. There is no other choice. And without this graph, we can't do reachability analysis. I haven't explained to you theoretically why, but I hope it's intuitively clear that if I have that static graph, which just says that it will reduce by 1, I need some extra bookkeeping to do reachability analysis, right? Yeah. Yeah, I mean, you are allowed to refill provided the number becomes less by even 1. These things represent that. Just some random choices of refill. So here you are allowed to refill, here you are allowed to refill. But you could remove all this and you say I'll refill only from here. That's also all right. I think this particular model, I picked it up from a textbook and that allowed refills anywhere in between. That's about it. Right? So is it clear? So this is what we mean. So in general, now you are able to understand why model is big and what happens. So this is still a very small toy example, right? It is still not anywhere close to even a realistic example as a toy example, and you can already see beyond this. If I put 3 cups of coffee, 3 cups of tea, I can't draw it in 1 slide. It goes, and you can imagine the size, right? It will be, the order of magnitude is exponential. It's a factorial, and there is nothing much we can do about it. So the early model checkers, which came in the 90s, actually did explicit state space search. They would take a program graph, they would draw a transition system like this, and then they would just deploy what slightly cleverly implemented breadth first search. Depth first search may not be a wise idea because in an infinite graph, because you could go down one path and get lost without coming back. So you have to do breadth first search. So they did clever breadth first search. They did what is called breadth first search on the fly. They wouldn't generate this whole graph, put it in memory, and then do breadth first search. As they want to do BFS, they would generate on the fly. And they were working fine, and it was running for many years. And then in the late 90s, obviously this didn't scale to model any kind of realistic systems. And that's what the second part that I was talking about, right? A team at Carnegie Mellon University developed a very nice data structure to succinctly represent these kinds of large graphs. That data structure is called binary decision diagram, and that model checking technique is called symbolic model checking. That's what got, the student did the work, the advisor got the Turing Award, right? So Ed Clark got the Turing Award for Ken Macmillan's thesis on symbolic model checking. So anyway, so that symbolic model checking is what is currently in use. But what we will see is an algorithm that will do an explicit state search, because it's still interesting from graph theory point of view. And there is another tool called Spin, which is an open source tool, which still does explicit state search and is in use. So there is need for even algorithms that do explicit state search, right? So that was, I'm not formally defining what a transition system corresponding to a program. This is the unfolding. I will skip the definition of an unfolding, but you understood, right, from the example what we mean by unfolding. It will be a large graph. Yeah.
The unfolding done by hand or code generation?
The tool like Spin would generate it. It doesn't generate, as I told you, it doesn't even generate the whole unfolded graph. It generates it on the fly. As and when it searches for it, it generates it. But there are other tools, symbolic model checkers like NewSMV, which don't generate the unfolding as a graph. They generate an unfolding as a compact representation of a Boolean function. It's a completely different data structure they use. You can't hope to generate the unfolding for any practical system, store it in memory and run BFS on it. It doesn't work. Right? So the thing is, this is just a single system, a single toy example. Realistic systems are not single systems. they are actually concurrent systems that need to be verified. Like for example, if you take this autopilot, it's typically getting inputs from the weather, from terrain, from ATC, you know, it talks to a lot of other entities, gets input and does its processing. It interacts by sending, receiving messages and so on. Those are the kinds of systems that we want to verify. Concurrent systems are distributed systems. So there are transition system and program graph models available for modeling these kinds of distributed systems. I'll show you one example. We may not have time to do other kinds of things. So as I told you, many hardware and software realistic systems that we want to work with are concurrent or parallel in nature. They include several processes that run in parallel. Parallel means what? There are agents or processes that do their own computation, and then they will take inputs from other processes or agents. Like if you take this autopilot thing, there will be the main autopilot, which is a process that is running. It will communicate with the process that supplies weather data, with the process that supplies terrain data, with the process that supplies ATC commands, air traffic control commands, and so on, right? So they have to talk to each other in a distributed system. In classical operating systems, distributed systems terminologies, there are 3 or 4 standard ways of talking to each other. One is they don't talk to each other at all. That's the first one. It's the simplest thing, right? Usually you might wonder why do they exist if they don't talk to each other, but when we develop the theory, we develop it because otherwise somebody else will write a paper that talks about they're not talking to each other, right? So if you have many processes, they have the choice between talking to each other or not talking to each other. So not talking to each other at all, that's the first one. No communication between the processing entities. The second one is processes talk to each other, but they talk to each other by either synchronously or asynchronously, right? What would be easier example is asynchronous. Asynchronous is basically there are buffers or channels available, and processes talk to each other by sending messages on the channel and receiving messages from the channel, right? Our cellular communication works like that. The explicit buffer is available, and somebody sends it, somebody receives it. If the channels are FIFO, it goes in order. If the channels are non-FIFO, it gets garbled. That's all right. But there are channels available. The other is there is a notion of a global clock, only one global clock. In a typical small system, there will be only one global clock. Like for example, in a car, all the software in the car will run if the, like for example, if you have things like cruise control system in a car, which is available in a lot of cars abroad, where you are, so you don't have clutch and this thing, you just have this PNRD, parking neutral reverse drive, right? So you can appeal to the cruise control system to maintain a standard speed of 25 miles per hour, right? So how will it know 25 miles per hour? How will it know whose per hour? Is it the per hour of the driver's watch? If tomorrow some other driver is driving, is it the driver's watch? Obviously not. It's just one clock. It's the GPS clock, right? So there is one global clock, or that is the car syncs up, and all processes sync and work on that one global clock. So they will do an action at one tick of that clock. That tick could be at 12 hours, that tick could be at 13 hours or whatever. So that is synchronous communication, right? So there is a notion of one global clock, and all processes have a common set of actions that they execute at a particular time tick. If you've done a course in operating systems or distributed systems, you would have seen these models. This one is one clock, and they all execute action synchronously at that clock. This means that they have buffers or channels. They communicate by exchanging messages on the buffers or channels. This is the model that we saw now. They have shared variables, and that increment, decrement, and reset example that I gave you yesterday, that is the third one. They all communicate by reading the value of a set of shared variables and writing to a set of shared variables, right? So these are the 4 ways of communicating if processes interact in a distributed system. So typically interesting systems that we want to model check or verify will be concurrent systems. So we need to specify how the global system will look like if processes work synchronously, asynchronously, if they do shared variables, if they don't communicate at all. Because if we don't look at the global system, like we did yesterday in the toy example of increment, decrement and reset, we'll make mistakes. Only by looking at the global system will we know what is happening, right? So in the theory of formal methods, there are standard operations defined on transition systems that tell you how to define global system in each of these 4 cases, right? So I will just tell you one, but feel free to contact me if you want to understand the others, or I can point you to textbooks or references that talk about others. So it's very important to look at concurrent systems, and when we look at concurrent systems, we have to look at how the processes or agents in a concurrent system communicate, 4 ways of communication, and for each of them, there are transition system program graph semantics available. So this is how it will look like. Assume that each individual process is modeled as a transition system TSI. There are n processes. So I have TS1, TS2 and so on up to TSN. The goal for us is to be able to define a parallel composition operator. Usually in computer science we write like this, two lines, 2 vertical lines. Not to be confused with the programming language OR. This has got nothing to do with that. It's called the parallel composition operator. So the idea is to define a parallel composition of all these n transition systems, TS1, TS2 and TSN. And if the TSIs communicate by using shared variables, then this operator will take a particular flavor. If the TSIs communicate by sending and receiving messages on a channel, then this operator will take a particular flavor, and so on. Or it could even be the case that suppose there are n processes, 2 of them will communicate over a global variable, 3 others would communicate using message passing, and one of the 3 that communicates using message passing could do a shared variable communication with a 5th one. You're able to understand? It's not like all n of them will always follow one type of communication. That's too unrealistic a world to be in, right? In general, there are 4 types of communication available, and between the n of them, they could choose anything they want. It's completely based on the designer who designed that system. So we have to be able to be ready to define the semantics of those, right? In realistic world. But I'll show you just one example because I would like to show you how model checking works. But so this is what I said. The above scheme can be iterative. One or more of the TSI can be a transition system that's obtained by a parallel composition of other transition systems. This one could mean that there are 2 other transition systems that communicate using message passing. It could be several layers of communication. So as I told you, there are 4 ways. I'll show you the first one. It's still useful. No communication. No communication in the sense that the system runs on faith. There are models like that do. The system completely runs on faith, right? So we'll see what that is. So the simplest toy example that I could think of is models of 2 traffic lights on roads that don't intersect. So they're just separate, right? So they don't have to communicate at all. So traffic lights switch completely independent of each other. I mean, this is a toy model, but there are realistic models of examples that don't communicate at all. If you want a realistic example, one concrete example that I can give you again from the avionics domain, because I work a lot in that domain, is so in avionics there are design paradigms that are recommended. One of the design paradigm is what is called time and space partitioning. So in an operating system, in a real-time operating system, which is an operating system of a specific kind that runs as a part of an embedded processor, so what happens is that processes are bundled together in, so they don't share memory locations. The memory location is partitioned. So there are disjoint memory locations available, and processes that run within one partition cannot talk to processes that run within another partition. So this is a classical operating systems paradigm that's called time and space partitioning. In fact, a part of the Android mobile OS, right, that also has time and space partitioning built into it. So when processes do time and space partitioning in RTOS, then they don't talk to each other. They still work. So that's a non-trivial example of an interleaving. I don't know whether I made sense or not, but you could just go back and Google for time and space partitioning in an RTOS, you will get, or even time and space partitioning in Android or something like that. It's a standard concept in operating systems where the processes are partitioned in both time in terms of their execution and space in terms of their memory location. So this is a toy example that we have of, so there are two traffic lights. This is process 1, this is process 2. Here is a toy transition system for process 1. I have not even put amber or yellow. It just goes between red and green infinitely often. This goes between red and green infinitely often. They operate on two roads that don't have any intersection, right? So what will be an interleaving? You just talk about anything, right? The first one could be red, the second one could be red. The first one could be green, second one could be red, or the other way around, or both could be green. You're able to understand? So these are the two small transition systems. This is the global transition system. How do I get the global transition system? So this is a graph. This is a graph. You take what is called the product of two graphs, which is you take products of states, Cartesian products of states, and you take Cartesian products of transitions, right? The normal set theoretic Cartesian product. So this is how it's defined. So if I have two transition systems, TS1, TS2 given like this, states, actions, transitions, atomic propositions, labeling function, then the global transition system is the cross product of the states of this and this. Actions could be the union of actions of this and this. And initial state is the initial states of these two. Atomic proposition is the union of atomic proposition of these two. Transition relation says that an ordered pair S1, S2 will move to an ordered pair S1 prime, S2, provided the first transition system moves from S1 to S1 prime on this action. It's just independent, right? So you say a pair moves if one of them moves, right? I'm purposely moving fast. Don't worry about too much of the notation, but get the intuition, right? What I'm trying to say is that if I have two transition systems like this that don't talk to each other, I say if this one moves from here to here, the global one will also move. This one moves from here to here, the global one will also move. No problem, right? So that's what is captured here. So you take the cross product of the two states. You say an ordered pair moves on an action alpha to another ordered pair if one of the transitions is respected by the first transition system, right? Actually, this if you studied automata theory, you would relate this as the construction that you do for closure under intersection and union. It's a standard thing. You take the cross product, right? That's because you want both. You want to accept the union or the intersection of both the languages. So you take cross product. That's the same construction that we are doing, right? So here is another example. There are two independent value assignments. Let's say x is x plus 1, y is y minus 2. So there is some variable. They're not dependent on each other. There's one transition system where x is x plus 1, that's given by alpha. Beta says y is y minus 2. So this is one action. If x is 0, then if I execute alpha, then it becomes 1. If y is 7, if I execute beta, then it becomes 5. Because these two are not independent, I can do the global system. In the global system, x is 0, y is 7. If alpha executes, x will become 1, y will continue to be 7. If beta executes, x will be the same, y will become 5. So after alpha, one more alpha can execute. I have not modeled that. But suppose after alpha beta executes, then y gets 5. Suppose after beta alpha executes, then x becomes 0. You can go on like this. Because they're independent of each other, it's just taking the cross product, right? All possible combinations of each. This is the simplest model. Similarly, it's not easy to write these global transition system models. It will take me half an hour, 1 hour to explain. You can come up with models for the other three means of communication. Shared variables, then I told you, right, working on a common global clock and synchronously executing actions, or sending and receiving messages on buffers and channels. So we assume that buffers are of bounded capacity. If buffers are of unbounded capacity, you'll run into problems. So given transition systems and program graphs corresponding to individual processes, you can model the global transition system by defining some kind of this operation. This operation. For each of them, it will be of a different kind, and it's fairly complex to be able to do it. So just to summarize what we did till now, I don't know if all of you will be able to see the board, but I'll also talk about it. So we are looking at model checking. For model checking, there are two parts. As we saw yesterday, there is requirements on one side, and there is system on the other side. Right? The question that I want to ask is, does system, in the language we will write like this, satisfy requirement? So read this notation as, does system meet requirement? Does system satisfy requirement? This is the question that I'm trying to answer. So I have system modeled as a formal model in some language. Then I have requirements written formally in another language. And then I have an algorithm to check for this. Is this clear? This algorithm can be run on a computer automatically. If this algorithm is a pen and paper proof, then you're doing theorem proving. If this algorithm can be fully automated, then you're doing model checking, right? Literally at a high level. So what we saw till now is a formal model of a system. Not realistic systems, abstract systems. There are several formal models. I showed you two of them, transition systems and program graphs. Again, a system is just not one system. It is a composition of several systems. So I can still look at them as transition systems and program graphs. They are typically large, not small for realistic systems. And you can't model a full realistic system always as a transition system or program graph. Even if you, then it becomes so large that you can't handle it. So we typically abstract and model based on what we want to focus on. What we want to focus on, we go on and model. So we saw one, how transition system, how a program graph looks like, and one model of synchronization. Now I would like to spend some time on this part. How to write a requirement formally. We can't do with the system shall never hang. Server will respond to a request from a client within 3 seconds. You can't work with requirements like that, written in English. We need a mathematical language to write a requirement in for the algorithm to be able to operate on both and check, right? You could specify requirements as transition systems and program graphs, but if you're doing model checking, the most popular way to write a requirement is in logic. So most of you would have heard of Boolean logic or propositional logic. It's commonly taught maybe in the second year or first year of a computer science undergraduate degree, along with a course in discrete maths. But that won't be enough for our needs because we need a few other operators. And we all use a lot of logic, by the way. Whoever writes programming basically uses logic because you use things like these. They're all the standard logical operators. In fact, you use things like these over non-Boolean variables. You know, you can write x is less than 5 and flag is equal to true. You do things like this, which we commonly write as a label for an if statement, right? X is less than 5, flag is true. So what do you infer from this? X could be an integer. Flag is a Boolean variable. So this returns a Boolean value, x less than 5. This returns a Boolean value, and I can add two Boolean values to compute another Boolean value. And if that Boolean value is true, the program execution takes one path. If the Boolean value is false, the program execution takes another path. So we call these as relational expressions and logical expressions in programming language. In serious computer science, we call this predicate logic. So predicate logic is a logic that deals with variables of any type, and its goal is to be able to return numbers, right? So for us, for the purpose of model checking, predicate logic is good enough, but typically there are other popular logics for model checking. Predicate logic has a very old history in computer science. There are people like Hilbert and Gödel who thought that using logic you can answer all of mathematics, and then Gödel showed his incompleteness theorem, which says that using cleverly constructed arithmetic, I can construct sentences that contradict each other. So, but in 1977, there was this computer scientist, mathematician turned computer scientist called Amir Pinoli, who's also a Turing Awardee winner. So the one logic is, this kind of logic is used by mathematicians. We as computer science engineers maybe know them only for programming, but mathematicians have looked at them long ago. Another popular group of people who work with logic are what are called philosophers. Right? I mean, if you know anybody who has done an MA in philosophy, they would know logic, a good amount of logic, as much as a mathematician would know, actually, because they do look at what are called logics of knowledge, epistemic logics, few other logics. So basically, they talk about the abstract things which an MA in philosophy person would talk about. It doesn't take too much to imagine how abstract it would be. So you would need to reason about it logically, right? So there are logics that were popular amongst philosophers which had proper mathematical semantics, like electrical engineers know a good amount of abstract algebra, economics people know a good amount of maths, like that. Philosophers who know a good amount of maths focused on logic. So there was this person called Amir Pinoli who observed that you can take a particular logic that philosophers use and use it to write requirements in computer science. So for this observation, he got a Turing Award. Right? I mean, it was a non-trivial observation because it came early enough. So he knew enough of the logic that philosophers use. I mean, now the way I'm stating it, it looks so trivial, but at that time, I'm sure it wasn't that trivial. So he took this particular logic that philosophers used. It is called temporal logic, logic of time. And he said that, by the way, temporal logic is great for philosophy. It's been there for many years. I can use it to write specifications of programs. And once I can use it to write specifications of programs, I can come up with an algorithm that will do model checking. So this is what he did in 1977, right? So he passed away a few years ago, but he didn't come up with the algorithm himself. There was another person called Moshe Wadi, who's at Rice University. So he took Pinoli's logic, Pinoli's observation that you can use this philosophical logic to write specifications of program, and he said, okay, if you use this logic, here is an algorithm that will model check, right? So that's how it works. So what we will see is one such logic called temporal logic, right? One such temporal logic is what I will introduce you to. So that temporal logic that we will see is called Ctl. We'll see why. So before we move on, maybe I'll just take this example again. I hope all of you can read it just to motivate temporal logic. This is another toy example. We stay in the world of kitchen. So from a beverage vending machine, we've come to a microwave oven, right? So here is a transition system model of a microwave oven. So I'll just explain it to you what it looks like. There are 7 states in this model, so many transitions that you see. So read this little tilde here, that tilde-like thing that you see. That is another notation for not, for negation that we use. So negation could be written like this or like this. That's okay, right? So this is the start state, the initial state of the microwave. So it says not start, not close, not heat, not error. So what does it mean? It says the microwave has not yet started. The door of the microwave is not closed, which means it's open. Because the microwave is not yet started, the microwave cannot be hot. And the microwave is not in an error state. Is it clear what I'm reading out? So from there, if somebody closes the door, then the microwave is not yet started, the door is closed, not yet hot, there is no error. You're able to understand? And then somebody starts the oven. So the microwave has started, the door is closed, it's just started, so not yet hot, and there is no error. Starting means think of it as power button. I mean, this is a toy example. Just so somebody says, okay, start heating. There's a button for warm up. So then when I go to microwave started, doors closed, it's hot, no error. You're able to understand what I'm saying? And then somebody says cook, then something, it goes like this. and then it stays there for cooking. Then somebody opens the door, it goes there. And then what are the other things? Yeah. So if this from this state, if somebody presses the start button without closing the door, then the microwave has gone into an error. Something like that, right? You're able to understand the model. So this is an abstraction of the behavior of a microwave, right? So this is a transition system for us, right? And suppose we want to show that this microwave is working correctly, right? Just as a small case study, right? So this is the system for us. And what could be a requirement to show correctness? Can you give me some requirement about a microwave oven? Anything is okay. Just going by what we have, some requirement, something. Huh? Yeah, it can't get hot when the door is open. That's a valid requirement, right? You don't want it blasting microwave heat energy all over the kitchen. Anything else?
If you reach an error state, eventually you should reach a non-error state.
Yeah, the microwave cannot be in an error state forever. So if it reaches an error state, sooner or later, somebody will come and reset it and make it work again. Right? Anything else? Yeah. So by the way, temperature range, that's a good point. Can we specify any requirement about temperature range in this model? No, right? Because this is a transition system, not yet a program graph. I have 0 variables here. So I can talk about temperature range, but I have to add things to it. I have to add variables, make it a program graph, then I can talk about temperature range. Any other requirement? Sorry? Preheating. This microwave doesn't have that. Then anything else?
It should stop heating up after opening the door.
Sorry?
It should stop heating up after opening the door.
It should stop heating up after opening the door. Yeah. So I was looking for one example that relates to as the microwave starts working, as time progresses. Any requirement can you think of? Like one requirement is that if it goes into an error, sooner or later it will come out of it. So any other requirement about as time goes on, any requirement? Yeah, it should finish heating up after the specified time, yeah? Which loop, this one? Yeah, this one? It can't go on cooking. So sooner or later it should be done or whatever, right? Sooner or later it should be done. So that's a requirement over time, right? So what I'm saying is this. I mean, this is a yeah.
When it starts free to switch, which changes from way to bit.
Yeah.
So suppose if there's an error, we are not handling.
Yeah, that's true. So this is by no means is a realistic microwave. It's just very high. So in design, there is a notion of abstraction and refinement. So this is a.
We have to handle the error in each stage, right?
Yeah. So see, this is small enough to put in one slide. So that is just an entertaining toy example, not a. So it lacks a lot of details, right? But it's still good enough for us to understand what we want to say, right? So what I'm saying is for this microwave and for other systems, like other realistic systems, if you take, like for example, just to give you a better example, you must have heard of this thing called mutual exclusion in operating systems. You would have heard. There are lots of algorithms, Peterson's algorithm, Decker's algorithm. So basically there is a notion of a critical region computation, and when two processes are in the critical region, they should have mutually exclusive access to the critical region. Because if they have common access to a critical region, then there could be a data race, as they call it. Like we saw in that example yesterday, right? There could be a like increment, decrement, reset. There could be a race condition. So to avoid race conditions, you say that processes that access the critical region should have mutually exclusive access. One common simple solution to that increment, decrement, reset example that we saw to avoid data race is to put that two statements inside what is called an atomic, make them atomic. What do we mean is that once it begins checking for that if condition, it should execute the statement after that. No other process should intervene. So you make them atomic, execute in one chunk, then you ensure mutually exclusive access to what is called the critical region and avoid a data race. It's a standard thing in operating systems. So one requirement about mutual exclusion could be that if several processes are interacting, then they have, like other example that I told you, right? If several faculty are using a network printer, the print commands to the network printer should have mutually exclusive access to the printer. It is highly likely that two faculty members are giving a print command at the same time. It obviously doesn't happen that the printer prints one page of mine and one page of the other faculty, right? It queues it up and prints it properly. So mutual exclusion is a very common problem that comes at several places. And what would be a requirement for an algorithm for mutual exclusion? One is that no two processes are in their critical region at the same time. So this is one requirement, right? So if I state it in temporal logic, you say always. Always means at all times. It is the case that no two processes are in their critical region. So let's say you have, so whose job it is to ensure this? In the operating system, it is a scheduler's job to ensure mutually exclusive access. So there is a scheduler, right? You know what a scheduler is. So let's say you have a rogue scheduler. What do we mean by a rogue scheduler? It's not a good scheduler. So it says, yes, I'm doing mutual exclusion. But the way it solves mutual exclusion is, let's say three processes want to access a critical region, but it always schedules only one process. Or it's not being fair. So there is a notion of fairness in operating systems. So a scheduler that ensures mutual exclusion should ensure mutual exclusion and ensure that it is being fair. If a process wants access to a critical region, sooner or later the process gets access to a critical region. It cannot be the case that a process that wants access to a critical region is starving. So there is this notion of starving, they call it starving in operating systems. So a fair scheduler will ensure that there is freedom from starvation. So there is starvation freedom. So these are terms that they use. So how, if I reiterate what the requirement or the specification for a scheduler will be, it will be like, whenever a process wants access to a critical region, the scheduler should ensure that eventually, right, the process gets access to a critical region. So if you sort of focus on the words that we used when we wrote our requirements, we used words like always. Always means always, whenever the system works, this should be on. Here for microwave, always when it is heating, door should be closed. Always, right? Otherwise it's not safe. The microwave is not safe. So these are called safety properties. And then what would be fair, what would be an unfair computation for a microwave? So I'll come back to the microwave. In the context of an operating system, I told you, right, a fair scheduler is one that lets a process, whenever a process wants access to the critical region, eventually, means some point in future, in time, it will get access to a critical region, right? So here also, whenever a microwave is started, it should work, right? Somebody should start heating up. Like it cannot forever go from, these kinds of loops. You're able to understand. Imagine a child playing. Start the microwave, open door, close door, open door, close door. And you can't say that, see, I'm using my microwave, right? In operating systems, we call this live lock, right? Or busy wait. A process does a lot of computation, but nothing useful to anybody. So unlike, this is different from a deadlock, where everything stops. So live lock is, something's happening, but it's of no use to anybody. So we want busy waits to be avoided, we want starvation freedom, we want safety to be met. So these kinds of properties all deal with time. What notion of time? At all times. Means whenever the system is up and running, this should be the case. If this happens now, then at some time in the future, something else will happen. We want requirements like this. If this happens now, then in the next state, like for that beverage vending machine, right? If somebody inserts a coin, then in the next state means what? With a reasonable amount of time, 2 minutes, 1 minute, 50 seconds, I want coffee or tea, whatever I chose, or it will give me the menu, right? So these are the operators that we are talking about. Like for example, I'll just show you this. So it says read this as always, globally. A is for always, G is for globally. Globally means across the system. If a microwave is started, then always somewhere in the future it will be heated up. So it specifies that whenever a microwave is started, there will be one execution of the microwave where it's heated. There's going to be no child in the microwave where it presses start and goes open, close, like that. It's saying, I'm using the microwave. That's not going to be there. It's going to serve its purpose. So what this says, this is the other specification that we discussed about. Always globally, if the microwave is heated, then the door will be closed. So read this double-lined arrow as the logical implication, if then. If P, then Q. P implies Q. This is also implies, right? It's a normal propositional logic implication. P implies Q is not P or Q in logic, right? So this is what we mean by temporal logic. Clearly observed that for almost all systems that need to be verified, a temporal logic is good enough to write functional requirements, the kind of requirements that I told you yesterday, right? Not a requirement which talks about the dimension of a product, but requirements that talk about functionality. So Amit Neoli observed that almost all functional requirements of systems can be written using a logic that has operators that talk about time. Logics that have operators that talk about time are called temporal logic, temporal in the sense of time. And there are three kinds of logic, the basic logics that have operators that talk about time, LTL, CTL, and CTL star. So we'll show one logic. So this was Pignoli's seminal observation, post which an algorithm was given, actually. So I'll tell you about one logic called CTL. Yeah, so this is what I said. This is Pignoli's observation. He said temporal logics, which were used by philosophers, can be used to specify properties of transition systems. Another name for transition system is Kripke structure. Our interest is in specifying properties of reactive systems. I told you what a reactive system is. It's meant to be up and running all the time. And the properties basically describe a computation sequence. They talk about a behavior of a reactive system. And we'll understand temporal logics for this. So temporal logic, as the term states, was observed by Pignoli to be a formalism for describing a reactive system. So yeah, when you say temporal logic, we won't consider time explicitly. We don't mean 24th of June, 5:15 p.m. That's not what we mean. We mean it at an abstract level. We mean operators that facilitate reasoning about time. We don't mean time in the sense of actual time, right? We mean time in the sense of yesterday, tomorrow, somewhere in the future, always in the future, sometime in the past, in the philosophical sense, right? Not explicit time. So the temporal operators are things like this: eventually, never will this happen, and things like that. So they are temporal operators. They can be combined with the normal Boolean connectives, and or not, implies, if and only if, to form additional operators. So yeah, so we talked about this, right? We talked about having a transition system, and whenever there are variables in the transition system, I have not given, this is just a pictorial representation. We can't reason about this entity, we reason about the unfolding, right? The unfolding of a transition system is typically a tree, which is an acyclic graph or a forest of trees, and if the transition system has one strongly connected component, the tree will be infinite, right? So just one observation. So this means that you are at a particular state. Let's say taking that, maybe here, the second one, taking the microwave example. Let's say this means the second state of the microwave, that what was it? The door's closed and there is no error or something like that. And then from there, two different transitions could get enabled. Two different options could be there. So when you sit at this state, when you say always in the future something will happen, which future are you talking about? Future from here or future from here? Any thoughts? You're able to understand my question? Right? In an unfolding, when you're sitting at a particular state and say from this state always something happens, there are two futures meaning two possible executions that can happen from the state. Which execution are you talking about? Any thoughts? Yeah, so there are two answers only. One possible answer is I am talking about all the executions, in this case both the execution that could happen. Somebody else might say, no, I'm talking about one execution. So there is a choice of one or all. It's very simplistic choice, right? So when I could either consider the branching that is available from a particular node, or I say I don't consider all the branches, I consider one linear sequence at a time. This is clear? So those are two classical notions of time that philosophers reasoned about. When I am in a particular state, I could talk about two notions of time. So if you think about it philosophically, right, when I am in a particular state, one notion of time would be that, I live in Bangalore. Another notion of time is I take a flight and go to America, right? Or I either live in Bangalore, if I get my visa in the next 2 months, I will go to America. So if I go to America, some requirement will be true. If I live in India, some requirement will be true. So I could talk about, so time could branch. This is one philosophical notion. Another philosophical notion is no. You are one individual human being. You have one state at a time. You cannot be in India and in America. So you will go through a linear time as an individual. So you will either go to America or be in India. So there is a linear notion of time, right? This is philosophically. Similarly, from a state transition system, I could say sitting at this state, I will consider all possible computations, all possible future computations from that state, or I could consider one future computation at a time from that state, right? So these two notions of time are called linear time and branching time, right? They are called the same in philosophy, they're called the same in computer science also. So when you're looking at linear time, you're looking at sequences. So this tree corresponds to how many paths? There is this one path, there is one path like this, there is one path like this, there is one path like this. You're able to understand? I can take 4 paths. I can take them as 4 different paths, or I could take all the 4 paths together in this one tree, right? So the two kinds of logic are linear time logic and branching time logic. Time is linear, time is branching. So we will look at branching time logic. That branching time logic is called CTL. So CTL and CTL star. So it says sitting at a state, if I write an A, I mean all computations from that state. So for example, if I sit at this state, if I write a formula with an A, I mean all the futures from that state. And sitting at a state, if I write a formula with a E, then A stands for all, E stands for existential. So I'm talking about either this or this. I don't know which one. I don't specify which one, but one, any one from that state. So that's the outermost operator in branching time logic. So CTL stands for computation tree logic. So this unfolding is called the tree of computations. So that's the name for CTL, it's just branching time. So there could be two outermost operators, A or E, right? So using this, I could then say, okay, suppose I say E, sitting at this state, right? Then what I could do, I could go down this path, or I could go down this path, or I could go down this path, or I could go down this path, right? So then what can I talk about as I go down this path? I can talk about what happens always as I go down this path. What will happen sometime in the future as I go down this path. So there are 4 standard operators that are enough. So those 4 standard operators are these. In fact, 2 are enough, but we usually write 4. So it says what happens at the next state. That's X. What happens in the future or eventually, that's F. What happens always or globally, that's G. And this is until. Until says that sometime in the future it will happen, and until then this will happen. Sometime in the future I'll get a good job. Until then I will work hard. You're able to understand? So that is until operator. So there is, just to correlate, like for example in Boolean logic, do you know how many Boolean operators are there? 5. Somebody said 5. Only that much? How many different Boolean operators are there? Or in hardware circuit, which is same as Boolean logic, how many different gates are there? Huh?
3.
Only 3.
You can construct anything else.
So you can in fact you can construct everything else from only 2, not even 3. So if you talk, see, NAND is an operator, NOR is an operator, XOR is an operator. You can only, how many? 16 operators are there. So 16 different operators are there, but just 2 are enough to construct everything else. The 2 is, one is negation, you need that for sure, and between AND and OR, keep one of them. With just negation and one of AND and OR, you can construct everything else. You can construct all the 16 operators, actually, right? So similarly here in temporal logic, there are lots of temporal operators you can think of in the philosophical sense. Since this happened, from the time this happened, this has been the case. I am going to do this tomorrow, and from then on I will do something. You know, you can go on talking about like this abstract notions of time. What will happen in the past, what will happen in the future. But it was shown that to express all these abstract temporal operators that you can think of, these are enough. In fact, you don't even need these 4, you just need X and until. You can even get F and G from that. But usually these 4 are enough. So same thing like in Boolean logic, this just extends to temporal logic. This is a classical thing that we do. Like for example, if you, similarly in predicate logic where you have less than or equal to, greater than, if you just have negation and equal to and maybe one of less than or greater than, you can do everything else, right? Because you can write or this and then you can go on and on and on, right? Similarly between quantifiers, there exists and for all, if you have negation and one, the other one can be written. Like that, for temporal logic, just this much is enough, right? All the other temporal operators can be written using this. So the operators are, so what this says, read this as a property holds in the next state in the path. Read this as a property holds at some state in the future in the path. The third one is property holds at every state in the future in the path. The last one is until. It's the same as the English until. It says, like I told you, right? Somewhere in the future, I will get a job. Until then, I will work hard. So at some future, somewhere in the future, something holds. Until then, something else holds. This is another temporal operator. So just to put it figuratively, this is how it looks like. So let's say this is an unfolding. This is a pretty looking unfolding. It's a complete binary tree, but not all unfoldings will look like this. But in some unfolding of a transition system, what does this mean? E, F of G. Please remember, what did I say E was? E is exists from one futuristic path in the state. A is at all futuristic paths. F is somewhere in the future. G is at all states along the path. So if I have E, F of G from the initial state, there is one path where somewhere in the future small g holds. So that will be this figure. You're able to understand this blob, right? So there exists a path where somewhere in the future in that path small g holds. Read it like that, right? So here it says for all paths somewhere in the future small g holds. So how many possible paths are there? There's path 1, path 2, path 3, path 4. Right? So this is a binary, complete binary tree of depth 2. It will have 2 power n, right? Different paths, but whatever it is. So for every path, somewhere in the future, small g holds. Like for example, in this path, g held here itself. So in all the paths that come out of this, small g will continue to hold. In these 2 paths, g held here, right? So the third kind of operator is EG. What does EG say? EG says that there exists a path where g holds globally, throughout. So that's EG small g. Like it could be this path, it could be some other path. The last one says AGG. AGG is G holds everywhere. You know, it is like one of the 10 commandments. Thou shalt not lie, thou shalt not kill, kind of thing, right? Don't do it ever in your life. Always be good. That's what this is. This is in verification testing, we call these properties as safety properties. Autopilot will never crash a plane, right? Always, no matter what it is doing, it will never crash a plane. There will never be a state, so it will be always globally no crash. That's what will be true. You're able to understand? So it goes on like that. So those are called safety properties. The system will be safe. I will always have mutually exclusive access to the printer. Right? So these are the basic Ctl operators. So I'm not going into the logic because it will be a little confusing, but maybe I'll just quickly walk through it. Yeah, so this is the semantics of Boolean. So you start with atomic propositions that label the states. Then you say a negation of a formula holds if and only if the formula does not hold. Read this vertical line to horizontal lines as satisfies. The symbol is called satisfies. So in the transition system M, in a state S, when will small p, an atomic proposition, be satisfied? Like for example, if we go to the microwave example, so in this state, what are the propositions that are true? Start and error. In this state, what are the propositions that are true? Nothing. Everything is false. You're able to understand? In this state, what are the propositions that are true? Start and close. So that's what I mean by the semantics of this. So in the model M, at a state S, a proposition P is true if P belongs to the label associated with that set. In the model M, at the state S, negation of a formula is true if F is not true. This is the standard semantics of negation. There is nothing great about it. In the model M, at the state S, F1 or F2 is true if one of them is true. The standard semantics of logical OR. So what does this say? This is RE. In the model M, at the state S, EG is true if there is a path pi that starts from S in which G holds. Right? Similarly here, MS satisfies AG if for all paths pi starting from S, G holds. And once you have this, then you have the four operators. Next, future, global, until. Right? These always exist, the negation and OR. We won't revisit them. So what does negation say? In the model M, in a path pi, in the next state, G will be true. So the next state is given like this. It means that take the path pi, chop off the first state, start from the second state. That's the superscript 1. So this one says, in the model M, in the path pi, when will Fg hold? If there is some future in pi, such that in the kth state in pi, G holds. Right? Similarly here, in the model M, in the path pi, when will globally small g hold? If for all the prefixes, if all the suffixes of pi, G holds. And until is similar. So you say in the model M, in a path pi, when will G1 until G2 be true? In English, how will you read it? G1 until G2. Means somewhere in the future, G2 holds. Until then, G1 holds. Or G2 holds right now. That's also possible. I don't have to reason about G1. So that's what this says. It says that G1 until G2 holds if there is a k greater than 0, such that for that kth state G2 holds, and till k, that is from 0 to k, G1 holds. Right? This k could be the 0th state itself. So which means what right here G2 holds. I don't have to reason about it. So is this clear? I hope I wasn't too fast. This is basically all the operators that you have. So CTL and CTL star, there's a small subtle difference, but you can reason about it, and I'll show you examples of specifications and I'll stop at that. So now you should be able, these are not related to any of the examples that we saw, but some random functional specifications. So how do you read this? There is a functionality called start, there is a functionality called not ready. Says it's possible to get to a state where it started but not ready holds, which means somebody's just powered on the button, that's all. So what does this say? It says that always globally, if somebody puts a request, then sometime, always in the future, you should provide a acknowledgement. That's what it says. So this says that any device that you are operating on will get enabled infinitely often. So it says always globally. In the future, this will hold. So it means that it will get enabled infinitely often, right? So this says that this is what somebody said, no? From any state, it's possible to get to the restart state. Always globally, there will be a path that takes me to restart. Right? So like this, you can write lots of specifications, functional specifications about system. And it was Amir Pnoli who observed that you can use this logic to write specification. There are 3 flavors of this logic based on whether you consider, as I told you, all computations or one path at a time and how you play around with it. All of them are plus or minus. One has an algorithm that is p-space complete. One has an algorithm that is exp time complete. It's just a trade-off. Each algorithm has different running time, but I can model check using each of them, right? So this is just an example of a logic. So what I'll do next time is I will give you walk you through one model checking algorithm. So that might give you the complete spectrum of the results that exist as far as temporal logic model checking is concerned.